A bias network may establish exactly the collector current and collector to emitter voltage we want at room temperature. The central question is whether that operating point remains usable when the transistor is replaced, the temperature changes, the supply varies, or resistor values depart from nominal. In this lesson, we will connect Q point drift to distortion and thermal risk, define three stability factors, derive the leakage current stability factor for fixed bias and emitter resistor self bias or voltage divider bias, and use those results to make practical design decisions. By the end of the lesson, you should be able to explain why a BJT Q point drifts, predict the direction of movement caused by parameter changes, define and interpret the three stability factors, derive the leakage stability factor for fixed bias and emitter resistor self bias, and estimate total collector current drift. The emphasis is not only on obtaining formulas, but also on connecting each formula to the feedback mechanism and to safe active region operation. The quiescent point is the no input signal operating condition defined by collector current and collector to emitter voltage. It should remain in the active region with enough headroom for the required signal swing. Biasing establishes that point. Stabilization uses negative feedback to resist unwanted movement. This distinction is important. A circuit can be correctly biased at one temperature and still be poorly stabilized over component value spread and temperature. On the DC load line, collector to emitter voltage equals the supply voltage minus the collector current drop across the collector resistor. If collector current rises, collector to emitter voltage normally falls and the Q point moves towards saturation. If current falls too far, it moves toward cutoff. Either direction reduces the available symmetrical signal swing. Saturation causes compression, cutoff causes one-sided clipping, and excessive current can also violate the transistor power dissipation limit. Q point drift originates from both the transistor and the surrounding circuit. Current gain varies widely even among transistors carrying the same part number leakage. Current increases strongly with temperature. Base emitter voltage generally falls as a silicon junction warms. Supply regulation is not perfect, and resistor tolerances and temperature coefficients alter the loop equations. A stable design must tolerate all five mechanisms, not merely the nominal value of beta. In fixed bias, the base current is set mainly by the supply, base emitter voltage, and base resistor. Neglecting leakage, collector current is beta times base current. Therefore, when the base current remains nearly fixed, a higher beta replacement transistor produces a higher collector current. The output characteristic plot shows the operating point moving from Q1 to Q2 for the same base current setting. Collector current contains the beta times base current term and a leakage term multiplied by 1 plus beta. As temperature rises, leakage current increases and base emitter voltage decreases. In a poorly stabilized circuit, both changes can raise collector current. The additional current raises transistor dissipation, which can raise junction temperature further. Unless the bias network counters this positive electrothermal feedback, the process can progress toward thermal runaway and damage the transistor and circuit. A stability factor measures how strongly collector current responds to one parameter while the other parameters are held constant. The leakage current stability factor is dimensionless. The base emitter voltage factor has units of amperes per volt. The beta factor has units of amperes per unit beta. Lower magnitude means less sensitivity, so more stable, but the sign also carries physical meaning. These are local derivatives evaluated at the operating point. Begin with the leakage inclusive collector current equation and hold beta and base emitter voltage constant. The bias network may cause base current to depend on collector current, so take the relevant partial derivatives under those held conditions. Rearranging gives the general leakage stability factor. The partial derivative of base current with respect to collector current is the feedback term. If rising collector current causes base current to fall, that derivative is negative, the denominator becomes larger and sensitivity is reduced. For fixed bias, base current is independent of collector current. Therefore, the derivative of base current with respect to collector current is 0. Substitution into the general expression leaves 1 plus beta. With beta equal to 100, a leakage current change is amplified approximately 101 times in collector current. The result quantifies why fixed bias has poor thermal stability. The fixed bias collector current can be approximated by beta times the supply minus base emitter voltage divided by base resistance. Differentiation gives a negative sensitivity to base emitter voltage and a beta sensitivity equal to base current. The negative sign means that increasing base emitter voltage reduces the voltage available across the base resistor. More importantly, none of these expressions contains a stabilizing emitter feedback term. In emitter resistor self bias or voltage divider bias, the base network can be represented by its Thevenin voltage and resistance. The base emitter loop includes the emitter current drop across the emitter resistor. If collector current rises, emitter voltage rises. With base voltage approximately fixed, base emitter voltage falls, reducing base drive. This is the stabilizing feedback path that fixed bias lacks. Differentiate the base emitter loop with respect to collector current while holding base emitter voltage constant. Collecting the derivative terms gives the rate at which base current changes with collector current. The result is negative. A rise in collector current causes a reduction in base current. Its magnitude depends on emitter resistance relative to the sum of base and emitter resistance. Substitute the negative feedback derivative into the general stability expression. The resulting equivalent forms show the roles of beta and the ratio of base resistance to emitter resistance. If that ratio approaches 0, the stability factor approaches 1, the best theoretical value for this model. If the ratio becomes very large, the factor approaches 1 plus beta, reproducing fixed bias behavior. The graph plots leakage stability factor against the ratio of base resistance to emitter resistance for several values of beta. The trend is the main message. Increasing the resistance ratio weakens the base network relative to emitter feedback and increases sensitivity. A smaller ratio produces a stability factor closer to 1. In design language, a stiffer base network and adequate emitter resistance improve stability. Neglecting leakage current for these derivatives, collector current is beta times the Thevenin drive voltage divided by the base resistance plus 1 plus beta times the emitter resistance. Differentiation gives the two sensitivities shown. When beta is large and emitter feedback dominates, the base emitter voltage sensitivity approaches minus 1 over emitter resistance. The beta sensitivity remains positive but becomes small when the emitter term dominates the denominator. For beta equal to 100, fixed bias gives a leakage stability factor of 101. For voltage divider bias or self bias, with base resistance divided by emitter resistance equal to 10. Substitution gives approximately 10.01. Dividing the fixed bias sensitivity by the self-bias sensitivity gives about 10.1. Under the stated model, emitter resistor self-bias therefore reduces leakage sensitivity by roughly a factor of 10. For beta equal to 100 base resistance 240 kilo ohms and emitter resistance 1 kilo ohm, the base emitter voltage stability factor is minus 0.293 milliamperes per volt. Using the data in the table, for the temperature change specified, the change in base emitter voltage is minus 0.17 volts. Multiplying the two negative quantities gives a positive collector current change of approximately 49.8 microamperes. The sign is physically consistent. Falling base emitter voltage increases current in this bias model. This improved feedback bias circuit connects the base resistor between collector and base. If collector current increases, the collector voltage falls, reducing the voltage that drives base current. The circuit therefore develops negative feedback through both collector and emitter paths. For the stated values, the room temperature design gives a base current of about 35.5 microamperes, collector current about 1.7740 milliamperes, and base resistance about 121 kilo ohms. For this collector to base feedback example, the leakage stability factor is approximately 10.24 from the table. For change in temperature from 25 degrees C to 100 degrees C, the leakage current rises from 0.1 nanoampere to 20 nanoamperes. So the change in leakage current is 19.9 nanoamperes. Multiplication gives a collector current increment of about 204 nanoamperes or 0.204 microamperes. The collector current at 25 degrees C was 1.774 milliamperes, and now at 100 degrees C it is 1.7742 milliamperes. In practice, leakage current, base emitter voltage and beta may all change together. For sufficiently small changes, the first order total differential estimates the net collector current change by adding the three sensitivity contributions. Each term must reduce to amperes even though the three stability factors have different units. Preserve each sign, then recalculate collector current, collector to emitter voltage, active region headroom, and transistor dissipation. First, evaluate each stability factor at the nominal Q point. Next, obtain parameter changes across the required temperature range from the transistor datasheet or a validated model. Compute each contribution separately, preserving sign and units, then add them. Finally, recalculate collector current and collector to emitter voltage and verify active region operation and power dissipation. A low stability factor is useful evidence, but it is not a substitute for a complete check. The practical preference is usually a voltage divider bias network with emitter degeneration, not simple fixed bias. Make divider current sufficiently larger than base current so that base voltage is not strongly beta dependent while still respecting power consumption. Allocate enough emitter voltage for useful feedback and check every supply, resistor, gain and temperature corner. An unbypassed emitter resistor also reduces AC gain. A bypass capacitor across emitter resistor may restore AC gain while remaining open at DC, but its frequency response must be checked. The most common errors are treating beta as an exact constant, assuming every stability factor is dimensionless, ignoring the sign of the base emitter voltage sensitivity, and using a rough textbook temperature rule instead of data sheet information. Unit errors between nanoamperes, microamperes and milliamperes are especially dangerous. Finally, do not assume that a low numerical stability factor guarantees a safe design. Always check load line position, voltage headroom, power dissipation, and whether the linear sensitivity approximation remains valid. Q point drift arises from transistor spread, temperature, supply variation, and resistance variation. Fixed bias is highly sensitive because it provides almost no collector to base negative feedback. The three stability factors quantify different responses and do not share the same units. Emitter resistance makes the derivative of base current with respect to collector current negative reducing sensitivity. The best design is not the one with the smallest isolated number. It is the one that remains in the active region with acceptable gain, headroom, tolerances, and dissipation across all required conditions. Use these questions to check whether you can move between the physical mechanism, the derivative definition, the algebra, and the design conclusion. Explain the negative feedback sequence in words before writing equations. In numerical problems, write the units of every stability factor and convert all current increments to one common unit. After calculating collector current drift, always translate that value back into collector to emitter voltage, active region headroom, and power dissipation.